So welcome everyone. Today will be our last seminar in this quarter. We are happy to have Dr. Andrew Holbrook to speak for us. Andrew is a new assistant professor in our biostat department, and his research interest is in scalable Bayesian inference with applications in neural decoding and viral epidemiology. Andrew graduated from UC Berkeley in 2009 with a bachelor's in German and classical languages. That's very interesting. And in 2018, he received a PhD in statistics from UC Irvine, where he completed his dissertation, Geometric Bayes. It is an investigation into the intersections of differential geometry and applied Bayesian inference. For this work, Andrew won honorable mention for the 2019 Leonard Savage Award in Theory and Method, awarded by the International Society for Bayesian Analysis. Most recently, Andrew received an NHK Career Development Award to develop high-performance computing methods and model the global spread of viruses in a big data context. So I think prior to joining UCLA as a faculty member, Andrew has been here for 2 years working with Mark Suchard as a postdoc. Okay, so welcome, Andrew. We look forward to your talk.
Okay, great. Thank you so much, Jessica. And it's a pleasure to be with everyone today, even if it's only virtually. My talk today is divided into a couple sections. First, I'm going to want to get some intuition for the importance of global transportation networks in spreading viruses, and I'll use the example of the Spanish flu to give us that intuition. And then having established this, I'm going to develop a highly structured Bayesian hierarchical model for the spread of viruses along global transportation networks. And then because of the size and structure of my model, I'm going to need to review some of the more modern instances of Bayesian inference algorithms. But then because of the size and structure of my model, actually even the most modern of Bayesian inference algorithms scale poorly as a function of the number of observations. So I'll need to harness some cutting edge computational hardware in order to massively parallelize my Bayesian inference algorithms and scale my model to a big data setting. Finally, with my hierarchical model and my high performance computing framework, I'm going to combine them and apply them to analyze the global spread of seasonal influenza. And then hopefully there's time where I can actually enter in on some of my more recent work, and I believe it's work that's relevant to researchers in this department, where I'm trying to combine the molecular epidemiological approach of this talk with the spatial epidemiological approach as well. So the 1918-1919 influenza pandemic, known as the Spanish flu, infected 500 million people worldwide, and it killed upwards of 100 million worldwide. To give you an idea of its global spread, it killed 17 million in India, 675,000 in the US, and 400,000 in Japan. It was an AH1N1 subtype of influenza, and purportedly not more aggressive than previous strains, but its successful spread around the world has been linked to the First World War. On the one hand, you have soldiers who are in cramped conditions, poor access to hygiene, and then on the other hand, the First World War precipitated a boom in global human transport. To get an idea of the role that the size and scale of modern transportation may have played in the spreading of the Spanish flu, I direct you to the bottom left, where we have mortality rates in 4 major cities: New York, London, Paris, and Berlin in 1918, 1919. And we see that just at about the same time, there's an explosion in deaths in the fall of 1918. And it's questionable whether we'd be able to see such a synchronization of events were it not for the speed and scale of modern transportation. Actually, the exact sequence, there's room for debate about the exact timing and the sequence of the travel of the Spanish flu around the world. But what is known is that the main routes of the main routes of transmission were across the oceans, because at that time the dominant mode of human transport was ocean travel. So a good example of one of the main routes of transmission would be this nice arc across the North Atlantic connecting London to New York. And if we zoom in, we've got London to the east, we've got New York to the west, and then for good measure, for comparison, I've also included the smaller Canadian port town of Halifax, Nova Scotia. And if I do want to model the spread of viruses, then it's questionable whether using these naive spatial distances, as I'll call them, is actually going to be effective, seeing as the actual transportation networks seem to be need to be taken into account. So what we might do instead is we might define some sort of ocean traffic passenger distance. And here we say that two locations on the planet Earth are close together if there's a large number of ocean traffic passengers exchanged between these two locations, say each year, annually. And then what happens is a definition of distance arises that's inversely related to the amount of human traffic between the two locations. So now London and New York in the top left are close together. And then Halifax, Nova Scotia, again, smaller Canadian port city, is out on the periphery. So this might be a more effective space in which to model the spread of viruses. Now, what would be the relevant transportation network today for modeling the spread of viruses? Well, in a 2013 Nature paper, Brockman and Helbing said, well, it's probably air transportation networks. And they constructed a large network, a graph, where with over 4,000 nodes, where each node is an airport. And they said that an edge existed between two nodes if there were direct flights between the two airports. And then they said that an edge was long if there were very few passengers exchanged each year between the two airports. And then they said that an edge was short if there were very many passengers exchanged between the two airports. And then they defined the distance on this graph as the natural distance that arises from taking the shortest path between any two nodes. They called this the effective distance. And they looked at how long it would take different outbreaks, we'll call them, or different epidemiological events to reach countries as a function of this effective distance. So for example, in the bottom left, we have H1N1. Again, this time it's the swine flu in 2009. And the x-axis is this effective distance from their network. And then the y-axis is the number of days it takes the swine flu to reach the country from its start in Mexico. So we start in Mexico again, and we're very quickly in the US, which is close in terms of network connectivity, but it's also geographically close. So the jury is still out. But as we continue, we see this very nice, linear relationship forming. Next, we're in the UK, France, Argentina, Barbados, and then we can see way out on the other side of this vast network, Afghanistan. Now, one question though is how we might model epidemiological events without a clear beginning in space and time. So for example, can we use the methodology of Brockman and Helbing to analyze, say, the seasonal influenza? Because it behooves us to better understand the way that these viruses travel around the world. So some questions come up naturally. How should we characterize How should we quantify, and how should we estimate rates of viral spread? And then if we're able to answer this question, then can we actually ascertain whether certain subtypes of influenza, or any virus really, travel more effectively around the world? And if so, can we identify them? And then finally, because I'm a statistician, I always have to ask the question, how can I quantify my uncertainty with respect to my results? So to help answer these questions, the first thing I'm going to do is I'm going to develop a Bayesian hierarchical model. It's going to be a highly structured model for the spread of viruses along global transportation networks. And I covered it a slide ago, but I just want to make it a little bit more clear that our challenge is that we're given these pairwise air traffic distances, or these effective distances, as Brockman and Helbing call them, between big N viral samples all around the world. And then we're also given the evolutionary history of a specific viral strain. And that's going to be very helpful for us. It takes the form of a tree, by the way. For example, I've got this cartoon on the left. But it's going to be helpful for us because we're interested in how quickly the entire strain travels and utilizes global transportation networks, not just an individual viron. So again, we're tasked to use this data to discover how quickly the strain travels through this global air traffic space. And then we're going to want to quantify our uncertainty. So, okay, that's the challenge. I'm going to take a step back though and say, what if we're not trying to model a diffusion through a network? What if we want to model the way that a virus travels through, say, Euclidean space? Well, then what's the absolute simplest model that I can use in this situation? And that, I'd argue, is the Brownian motion. Now, one can simulate a Brownian motion by starting at 0 and taking steps forward, moving through time. And at each small infinitesimal step, I'm going to generate a small Gaussian kick in a random direction. Now, I like this Brownian motion. Yes, it's pretty, but I really like it because it's so simple. It's so tractable. And you can see this because actually the marginal distribution at any time turns out to be Gaussian. So as evidenced by the histogram starting to look more and more like the Gaussian PDF. So this is my ideal model if I want to model the diffusion of viruses through a space, simply because I understand it. Of course, I can make it more complicated. For example, if I want to model the spread of viruses through a higher dimensional space, I can stack independent Brownian motions on top of each other. I mean, I can even give those little Gaussian innovations, those little kicks, I can give them different variances. And then you can see how the variance actually begins to accord with a rate of travel through the space. We have a standard deviation of 0.5 on the left. We traverse less space than we do on the right with the standard deviation of 1. This is all has been formalized a very, very long time ago, but I'd like to review it a little bit just so that we can get clear about the object that I would like to use as my ideal model. So a standard Brownian motion, WT, is equal to 0 at 0. Its differences at different time points are independent for non-overlapping intervals of time. Its differences at different time points are actually Gaussian, as you saw earlier, and their variances are the difference between the two time points. And then finally, thought of as a function, each of these sample paths is continuous. Now, I want to establish this because the object that I want to use is what I'll call this general multidimensional Brownian diffusion, which isn't much more complicated. But if I stack a bunch of these univariate Brownian motions together and I get this bold WT, then I can pre-multiply it by a rate matrix sigma. And this model balances simplicity. It's still incredibly simple. I understand it very well, but also a certain amount of flexibility and complexity. But then the question immediately comes up, okay, if you want to model the spread of a virus using this x of t, then how are you going to compare the rates with this general rate matrix sigma? How do you say that one rate is more than another? And for that, I'd like to use a scalar quantity that arises from this sigma. So I want to use the trace of sigma. And I can argue for this rhetorically by referring to fixed laws of diffusion in physics, where the diffusivity or the diffusion coefficient is a scalar value that's proportional to the squared velocity of a diffusing particle. It's given in units of meters squared over time. Excuse me, an example is meters squared over time. It's given in terms of displacement squared over time. So meters squared over seconds, for example. We can write out the stochastic differential equation that we're dealing with. And then we can use a basic identity of the stochastic calculus called the quadratic variation that says that dWt squared is actually equal to our usual infinitesimal with respect to time dt. And all this is to say that I can plug all these values in, and then I get that the trace of sigma of my rate matrix is given in terms of displacement squared, dxt, inner product with itself, divided by time. So this is just a way that I can argue that if I'm going to select this general multidimensional Brownian motion as my model of choice, then I have a way of comparing between them a rate of diffusion by taking the trace of sigma. And I think that now is the part of the talk where everybody says that I've gotten ahead of myself, because all that I've said is how I can model a Brownian diffusion, a virus using a Brownian diffusion through Euclidean space. And then you say, well, you have said nothing about how you can adapt this Brownian diffusion model to the network realities at hand. And the first network that I need to adapt my Brownian diffusion to is this global air transportation network. So how can I do that? How can I use the Brownian diffusion and nonetheless adapt it to this network? So for that, I'm actually what I'm going to do in the next two slides is I'm going to specify my likelihood in the Bayesian framework using Bayesian multidimensional scaling. So let's say that our data actually take the form of this big bold Y right here. And it's a big N by big N distance matrix with elements Y of little n prime, where each one of those is the distance between two objects, n and n prime. So this could be the distance between two viral samples on the global air transportation network. Well, then I can model that pairwise distance as being Gaussian with a mean given by, and this is a very important point, where the mean is the Euclidean distance between two random variables, xn and xn prime, in Euclidean space. So you see that each object n and n prime on the network actually is given its own latent variable in Euclidean space. And then what I do is I truncate my Gaussian to be greater than 0 simply because distances are greater than 0. So if I condition on all of these latent variables, all big N of them, then I have a likelihood. And this likelihood, it takes a very specific form that's going to come up later, which is that if you just take the log likelihood, and if you ignore this sigma here, then you have a summation over big N choose 2 terms, where each term is a pairwise term. So it depends on two objects, on n and n prime. And if I zoom in and look a little closer, then this Rn n prime just has the Gaussian component, and then the truncation term, where this capital phi is just the usual Gaussian CDF that we're all used to. And I'm using the shorthand delta nn prime as that Euclidean distance, again, between two random variables in Euclidean space. So I'm going to use this to map from the air transportation network to Euclidean space, where I can then model my diffusions. And I want to show you another cartoon simply because I think that it's better to visualize this. I start with my network. I've got 4 nodes, A, B, C, D. And then, for example, I've got the distance, the pairwise distance between nodes A and nodes B. That's given by YBA. Then Bayesian multidimensional scaling probabilistically maps from this YBA to 2 latent variables, XA and XB. And then you can see all of the latent variables. We're going to pretend that we have a 2-dimensional latent space model. Then we've got all of our random variables. And I've actually, if you pay attention, if you look closely, then what I've done is I've actually reflected over the AD axis, and I've also rotated by 90 degrees clockwise. And I've done this in order to show you that the BMDS likelihood is invariant under these operations, simply because pairwise distances are invariant between these operations. And then finally, I've drawn some blue contours around my low-dimensional random variables in order to show that this is happening probabilistically. Okay, I've specified my likelihood. This is going to take me from this pairwise distance data to Euclidean space, where I can use my diffusion model that I want to use in Euclidean space. But what I haven't done is I haven't said how I'm going to actually adapt this diffusion model to the family tree, as it were, to this phylogenetic tree, this evolutionary history in the bottom right. Because again, I want to do this because I want to model that how quickly the entire family travels through this space. So this is the part of the talk. I've specified my likelihood, so now I'm going to specify my prior. That's the Brownian phylogenetic diffusion model. And I have by no means invented this, but it's a very useful tool. And here, what happens is this family tree, this phylogenetic tree in the top right, its topology and its branch lengths actually dictate the broader covariance of, say, these 4 diffusing Brownian motions. And it does this, again, I want to make formal how it does this. It does this in a very specific way. So we assume that we have a tree in this part of the talk, and we associate to each tip of this tree, this binary tree with big N tips, we associate to each tip a Brownian motion that's centered at its parent node. So X3 is a Brownian motion centered at X5. X2 is a Brownian motion centered at X4. And what this means is that if we condition on the parent's value, then say X3 is going to be a Gaussian with mean given by the value taken by X5. And its covariance is going to be this branch length T3 times that rate matrix that I introduced earlier in the talk. So one thing that you're going to want to notice here is that the covariance of X3 conditioned on X5 is actually larger than the covariance of X2 conditioned on X4, simply because T3 is larger than T2. Now, if we say that, that the parent nodes themselves follow Gaussian distributions in a similar way, then we can actually integrate out the unobserved X4 and X5. And we're left with a big matrix Gaussian, a big matrix normal random variable with dimensions big N by P, where big N is the number of tips in our tree and P is the dimension that we're modeling our diffusion in. Again, the smaller covariance, this P by P covariance, is again given by our rate matrix. And then our big N by big N covariance matrix has a very specific form, again, dictated by the topology and the branch lengths of this phylogenetic tree. So one simple example is that the diagonal V22, so that's the covariance, that's the variance of this X2 random variable, that's just T2 plus T4. So I'm done constructing my hierarchical model. We start with samples all over the world, viral samples. We move from these viral samples to consider their position on this global air transportation network. BMDS probabilistically maps from these pairwise distances on this network to latent variables. And then we put a prior on these latent variables given by the Brownian phylogenetic diffusion. Again, we're constraining these diffusions by this evolutionary history. And because of our use of this latent variable framework, we're actually going to find that Bayesian inference instantly becomes much harder, even for small amounts of data. Now, if we assume that our data are generated independently, conditioned on a global parameter theta, and then observation specific latent variables xn, and if we put prior distributions on theta and on our latent variables, then Bayes' theorem says that the posterior distribution of theta, conditioned on our data, is actually going to be proportional to the ratio between two integrals, where the integral in the numerator is an integral over all of the latent variables. And then the integral in the denominator is over all of the latent variables and then nested within an integral over the parameters. Now, what this means is that the integration domain and its dimensionality are actually going to grow with the number of observations, because with each new observation, we have a new latent variable. So even for small amounts of data, we're going to see that this latent variable framework causes the problem of Bayesian inference to grow more difficult linearly in the number of data points. And those of you that have attended a Bayesian talk, now you know what part is coming. This is the classic part where we say, okay, we're going to do Markov chain Monte Carlo, because, well, we can't do numerical integration at this scale. So one choice that we have is the classical random walk Metropolis algorithm. And here we're using it to sample from a two-dimensional Gaussian centered at 0, 0. And here's the sampling path starting at -3, -3. We slowly move forward, generating new Markov chain states over time. And you can see that although it does look a little bit like a drunken walk, that we're actually slowly moving toward the high density region of our target distribution. That said, it's going to take many more samples until we've actually constructed a representative sample of this target distribution. And actually, this problem is going to quickly, this algorithm is quickly going to become useless as we consider higher dimensional target distributions. So to actually scale our model to a big data setting, again, remember that the dimension of our target distribution grows with the size of our data set, then we're going to need to use something a little bit more cutting edge. And I like to use Hamiltonian Monte Carlo. So here we have the exact same target distribution. We're going to ignore this little tail here, and we're starting at -3, -3 again. And you see that actually within a small number of Markov chain states, we're already within the high density region of our target distribution, and we're effectively sampling there. And the reason that this works so well is because Hamiltonian Monte Carlo uses first order gradient information about our target density function. And because of this, you can think that Hamiltonian Monte Carlo is to MCMC as steepest descent is to optimization. And why is this the case? Well, Hamiltonian Monte Carlo works by doubling the size of our parameter space with this auxiliary Gaussian variable, bold P here. And we call this the momentum, as you'll see, and you'll see why shortly. And we say by construction that this Gaussian variable P, this momentum, is statistically independent from our target random variable X. We construct a Hamiltonian energy function by taking the negative logarithm of the joint distribution, which again, because by construction we have independence, it's just the product of the two densities. Taking the log, we then get the sum of two components. Here on the left, we have a potential term. If we're going to follow the, if we're going to use physical terms, we have the potential term, which is the negative log of the target distribution. And then we have the kinetic term here, which is this quadratic term involving the momentum. Now, HMC works by simulating, by generating new Markov chain states, by forward simulating Hamilton's equations here, where the important thing to see is that the update, the gradient of our momentum with respect to time is none other than the gradient of our log target density. So that's why I say that HMC is to MCMC as steepest descent is to optimization. Now, why is it MCMC if we can simply forward simulate this system? Well, we can't do it directly, so we use numerical simulation techniques. And these techniques involve the repeated evaluation of this gradient here. So that's one thing that they do. And because of the discretization, the numerical discretization, error arises. And we need to correct for that error using a Metropolis accept reject step. So there we have to not only need to compute the gradient in the forward simulation, we also have to compute the posterior distribution in the accept reject step. The benefits are that HMC computes high dimensional integrals, loosely speaking, and it scales to tens of thousands of parameters. Again, the challenge is that HMC necessitates repeated computation of the log likelihood and its gradient. And in the best situations, this is linear computational complexity in the number of data points. And then if we are considering our specific model, well, what about our likelihood, the Bayesian multidimensional scaling likelihood? Well, it's worse than linear complexity. It's actually quadratic complexity, which is going to be horrible in a big data setting. And to see that, again, I mentioned it earlier, but if we take a look at the log likelihood, well, then it's this summation over big N choose two terms. And then the gradient itself that we're going to use during the simulation of the Hamiltonian system, this is also quadratic in the number of data points. And to see that, if we take the gradient with respect to a single latent variable, xn, then, and we pass through and we simplify things a little bit, then we can see that it's actually a summation over all n prime not equal to n of this pairwise object right here. So that's big N minus 1 terms. And then we actually need to compute the gradient with respect to all of these big N xn's. So that's going to be, again, quadratic in the number of data points. I'm going to present a solution, but before I do, let's just recap how we got here, because there's a lot of moving parts going on. Our goal is to quantify and infer the diffusion rates of global contagion. We want to use the Brownian diffusion model because it's a useful model. And basically, it's simple. We understand it. It's tractable. However, the Brownian diffusion model that we want to use does not account for network structures. We propose and we develop a model that adapts Brownian diffusions to the network realities, to the phylogenetic tree, and to the global transportation network. But for us, because of our use of latent variables, model inference is hard. The integral dimension grows linearly in the number of data points. So then we propose to use HMC. It's a powerful tool for Bayesian inference, and it scales inference to tens of thousands of dimensions. But then at the same time, HMC for our specific model, it's quadratic in computational cost in the number of data points. So we seem to have hit a wall. And now I just want to hint at the solution that I'm going to provide. If we just look at the likelihood here, if we just look at this summation over big N choose 2 terms, well then what we might notice is that each one of these terms is a pairwise term, and it doesn't depend on any other terms. So the idea is that if we have some sort of magical computer that can evaluate all of these terms at once, then we might be able to quickly compute the likelihood by evaluating all these terms at the same time and then summing over them quickly. And if we want to actually do that, though, in practice without the use of a magical computer, then we actually have to use some different hardware. And we can use either a CPU, or we can use a more developed, a more cutting edge graphics processing unit to actually do our parallelization. The CPU, you can use a multi-core approach. Here you're using anywhere from 2 to 60 cores, and this is usually nice simply because you can do completely different tasks at any time. Or you can also, on a CPU, you can also do something called vectorization, or SIMD, single instruction multiple data. And this is very different from a multi-core approach, because here, instead of doing instead of doing completely different tasks, you're actually carrying out the exact same instruction set over a vector of inputs. Or you can use a graphics processing unit. And here you're using thousands of cores, so it's often referred to as a many-core approach. But the restriction is that you're really doing something very similar to SIMD, or NVIDIA likes to call this SIMT, single instruction multiple threads. Again, you have the same instruction set that you're applying to different batches of data at the same time. And then just for those of you who haven't dealt with the GPU in the past 10 years, now current day GPUs have very high memory bandwidth and have been scaled to handle the big data setting. So what does the computing of the Bayesian multidimensional scaling likelihood look like on a GPU? Well, for that, I'm going to just present this picture as a single instance of thousands of instances being carried out at the exact same time. So any parallelization that you actually see in this picture, you can think of as being an additional form of parallelization, giving even greater speedups. So we draw 2 batches of our locations data, of our latent variables, from discrete batches in global memory. And we write them to be together, close together in shared memory on chip, on the GPU. Now that they're close together, we actually quickly evaluate their pairwise contributions to the BMDS likelihood. And we can do this in parallel, all at the same time, on chip. And then staying on chip, we can actually carry out, we can sum over all of these contributions to the likelihood to create partial sums. And we can do this extremely quickly on chip. Again, this is an additional level of parallelism. We do this using a binary reduction. And the binary reduction it gives you an additional speed up because it's addition, but it's logarithmic in the number of inputs. So we start with 4 inputs, and in a single cycle, we're down to 2 that we need to sum over. And then in one more cycle, so in 2 cycles total, we've moved from 4 objects to a single object. And that's our partial sum. And then we write this partial sum to global memory. And once we're back on the CPU in global memory and we have a small number of sums, we just sum them up the classical way. It's fast enough. So we can plug these into HMC to get some speedups over a single core processing. Here, our baseline is actually is a single core AVX, and we're looking at the speedup by evaluation type, the likelihood and the gradient. Single core AVX is just it's just kind of a widespread way of using SIMD, that vectorization on a CPU. And the first thing that I want you to see is that if we do without this vectorization, if we do no SIMD, then we're more than twice as slow. Although this is precompiled, so this is still going to be faster than using R, for instance. As we add CPU cores, we get speedups indicated by this nice arc, but these speedups, we witness what looks like diminishing returns. If we choose to use a GPU instead, then we get 100-fold speedups for our likelihood computation and 200-fold speedups for our gradient computation, where orange is the likelihood, gradient is blue, and I'm showing them as flat lines over the top simply because we're not using CPU cores, we're using thousands of GPU cores. Now, instead of looking at the relative speedup, we can look at how many seconds each evaluation type takes. So the likelihood on the left, the gradient on the right. And we can look at this, the number of seconds each evaluation takes as a function of the number of data points. And the first thing that I'd like you to notice is that we get this nice quadratic scaling that the math predicted, right? So we see what we would expect to see. But then we also see that as we add cores, so from 1 to 2, from 2 to 4, from 4 to 6, that as we add cores, we are getting speedups. Our evaluations take less time. But if we look closely, we might actually also be observing some diminishing returns as we add cores, as we add CPU cores. And then along the bottom, we've got the GPU results, which are basically flat at this scale. If we zoom in and if we actually ignore our CPU results, then we would also see a quadratic scaling. But, you know, at this scale, the GPU takes negligible time. So the upshot is that we can actually use this parallel computing in the context of HMC. And with this high performance Bayesian computing framework, then we can apply to analyze the global spread of influenza using our hierarchical model. Now, the data that we want to use in this example, we have over 5,000 viral samples from 189 countries collected between 2001 and 2013. On the left, we have influenza type A. On the right, we have influenza type B, where type A is generally regarded to be the more virulent type. It's associated with more deaths annually, with higher mortality annually, and it's also associated with the major pandemics, the major historical influenza pandemics. We have subtype H1N1 and subtype H3N2. Again, H1N1 was the Spanish flu and the swine flu. And then for type B, we've got Victoria and Yamagata lineages. And then for these subtypes and for these lineages, we have roughly 1.3 thousand for each of them. The first thing we do is we convert our locations data into 5.4 thousand choose 2. That's about 14.5 million pairwise distances, pairwise air traffic distances. And then before we apply our framework to analyze this data, we have to make a single modeling decision. And this modeling decision is how many dimensions should our latent space be? So for that, we're going to use five-fold cross-validation. And what we do is we train our model on a subset of the data, and then we evaluate the likelihood on the held out data. And you can see that we get fairly convincing results. For the two-dimensional model, our loss is 7.1 million. For the four-dimensional model, our loss is 3.4 million. And for the six-dimensional model, our loss is 2.8 million. If we go up to 7 dimensions, all of a sudden our loss shoots up again. So for this reason, we select the six-dimensional model. We then use, as planned, we use HMC within Gibbs to generate 2 million states for all of our latent variables given by bold X. And this is the important part, we've got 4 influenza strains. We're going to learn a different rate matrix, sigma, for each of the strains. And then something that I'm not going into in great detail in this talk is that we're also going to learn phylogenetic trees that I denote script T. And we can actually just visualize these trees. And here we've got 4 posterior trees. Each one of these is a posterior sample. Again, I'm not going into how we're actually doing this inference. That's for a completely other talk. But what we have done to better visualize what's going on here is we've colored each one of these posterior trees. We've actually colored them by the first latent dimension of our air traffic space, of our latent Euclidean air traffic space. So if a tree is more multicolored than another tree, then you might think that maybe this virus is traveling more quickly through this air traffic space. And to actually get that intuition, you have to zoom in. So here we've got H1N1 again. And what you can see is that even for somewhat large clades, for example, this one up here in the upper right, which is all green, this one over here is all green, this one is mostly purple. Even for somewhat large clades, these are groups of branches, you actually have pretty uniform coloring, suggesting that in these time frames, that this part of the strain, that these viral samples are actually staying relatively close together in the same neighborhood of this air traffic space. Pardon me. Just got an Adobe Flash reminder. Okay. If we look at H3N2, on the other hand, the first thing that you're going to notice is that it has more of a fine combed structure compared to H1N1. And then the other thing that you'll notice is that even in its smaller clades, that you actually get more of a multicolor tendency coming out here. And this suggests that even within small periods of time and small explosions of evolution, that H3N2 is traveling throughout this latent air traffic space. And then the question is whether we can actually formalize this intuition that somehow H3N2 is better using the air traffic space to travel around the world. And this is precisely why we put so much work in earlier in the talk to figure out what scalar value we can use to actually compare rates of travel between our viruses. So recall that we chose to use the trace of sigma, the trace of these rate matrices for the, and we called this the diffusivity, and that it took units of squared distance over time. So squared displacement over time. Then if we visualize the trace of our four different, the posterior distributions of our four different rate matrices, then we can look at their posterior densities and we see that H3N2 is actually far and away larger. And here, again, the x-axis here is what we're calling this squared, it's a mouthful, but it's the squared effective distance units per year. The effective distance is this network distance. And then again, it's squared displacement over time. So we see that H3N2, in accord with our intuition that, from the previous slides, seems to have a much larger diffusivity than the other three subtypes. And then why this might be the case, it's unclear. But one issue with H1N1 is that it tends to infect children and young people in greater amounts than it does the elderly and the middle-aged. So, but H3N2 tends to infect more evenly across age groups, and it's precisely adults that tend to use air travel and tend to travel more. So this could be one reason why H3N2 appears to travel more effectively, but really further analysis would be necessary to really tease this apart. And then finally, this is more of a sanity check. Well, what if we don't use a 6-dimensional model? What if we use a 2-dimensional model? And we just look at a single posterior sample and we look at the way that the different countries arrange themselves in our latent air traffic space. And if we do that, then we see exactly what we would want to see. That is, we see that the major world economic powers are all clustered close together toward the center, each one representing its own regional block. And this is what we would want to see because these are precisely the countries that feature the most air transportation and the most air transportation between them. So for example, we've got the US and Canada representing the Americas in the bottom right. We've got Germany, Great Britain, France, Netherlands representing Europe in the top right. We've got Indonesia and Thailand representing Southeast Asia to the left. And then to the bottom left, we have China, Japan, Korea, and Hong Kong representing East Asia. Again, this is just a sanity check showing us that this space kind of looks like how we would want it to look a priori. So I don't know, I've covered a lot of ground. Now might be a good time to take some questions, or I can also just move forward to the next part of the talk.
I've got a question, Andrew, if that's okay.
Sure.
So you're using the airport travel to figure out these distances, correct?
Yes.
Although, but presumably your actual, viral samples were not taken at airports, right? Or were they?
Yeah, no, they were not.
Okay, so how do you then, find a coordinate for a particular sample
Sure.
if it wasn't at that airport?
Sure. So you can do, you can just assume that it's collected at an airport and just do the closest airport,
Okay.
depending on kind of the precision of your spatial data.
Mm-hmm.
Or you can just collapse across countries, which is actually what we did here.
Okay, cool.
Yeah.
Thank you.
Any other countries? Any other countries? Any other questions before I move on? Okay. So I would argue that what you've seen in the first part of this talk was is sometimes referred to as molecular epidemiology, where you're actually relating traits or even the geographical diffusion of viruses to their phylogenetic tree, to their evolutionary history. There's other methods for modeling the spread of viruses. One that actually there are people at UCLA statistics that are really world experts in this, are the use of the spatiotemporal Hawkes process. And here, instead of modeling, here you're actually modeling the self-exciting dynamics of this virus. And you use this, you use a base process, which is just an inhomogeneous Poisson point process. And then you say that conditioned on an observation, that you have a higher probability of observing a future observation soon after and close by in space. And these self-exciting points are shown here in blue. Now, I'm not going to go too much into the details here, but what I want to say is that there are some striking similarities and differences between these two approaches. Now, the first similarity that you're going to see is that if I look at the likelihood of the Hawkes process, and I write it a little bit abstractly, then you kind of get this double summation over these terms that have these pairwise dependencies, here denoted n and n prime, similar to what we saw with BMDS, with the Bayesian multidimensional scaling model. So the first intuition is that, well, you know, Bayesian inference and actually statistical inference for the Hawkes process should be equally amenable to the GPU parallelization approach. And that's exactly what I've shown in actually 2 recent papers. And here, I'm not going to go into the details here, but all that I want you to see is that, well, these figures, they look a lot like figures that I previously showed you for the scaling of these evaluations for the Bayesian multidimensional scaling model. So that's the first thing. And then the second thing that I want to say is that actually inference for BMDS and for the spatiotemporal Hawkes process, that both of these can often be framed as these kind of, as simulating an n-body problem with pairwise potential. Again, you got these pairwise terms. And this was very clear in my most recent paper, where I wanted to model the self-exciting nature of gun violence in Washington, D.C. But I had extremely spatially coarse data. So my data was coarsened up to from being, so you can imagine that I'm throwing away any precision that goes beyond 100 meters in any direction. And I showed recently that, well, I can simultaneously infer the parameters that guide my self-exciting process. I can simultaneously infer those with the actual locations of individual events. So just to briefly go through this, I've got 3 pictures here. I've got 3 cartoons. And then in each cartoon, I've got in gold, these big gold circles are my explicit data that I observe. But this is coarsened data. So I've shown that I can actually infer the locations. And here we've got posterior samples from MCMC in the different colors for the different events, different gunshots. And so I've shown that I can infer these locations at the exact same time that I infer the parameters that guide my Hawkes process. And I've gone through all of this work simply because spatial data for viruses and for viral samples is usually extremely coarse. So if I'm going to want to apply the spatiotemporal Hawkes process to this viral data, then I'm going to need to overcome this spatial coarsening that you see here. So these are some. This is kind of giving you a forward picture to kind of where my research is heading over the next year, over the next couple years, as I seek to combine the spatiotemporal, spatial epidemiological approach with this molecular epidemiological approach that I presented earlier in my talk. Thank you.
Thank you very much for your talk, Andrew. This is a very comprehensive overview of the whole topic, I would say. Yeah.
Thank you. I hope I didn't go too far over.
No, I think it's a very good lecture for our graduate students. So now I think it's time for questions.
Wonderful.
From the audience, yeah.
Feel free to ask.
Any questions? Yeah.
It's just, there's so much going on there and you could ask all sorts of questions.
So maybe I can go ahead and ask the first question, a very big question, big picture question. So what is the advantage of doing Bayesian MDS in this context for this application? I'm just curious about that, instead of the frequentist MDS.
So I mean, I could give you some responses that you might actually not. So the first thing is computational complexity. If I want to do, and if I want to do classical MDS, then that actually involves, a matrix decomposition. That is cubic in computational complexity. Then again, so not to argue too strongly against it, that decomposition only occurs once. Now, one thing that is not my strength is kind of multi-stage inference. So if I want to perform that classical MDS and then model the results of that arise from that decomposition, which is really just a special case of PCA, then I'm not really sure how to model those in the latent space. And under the Bayesian framework, just using a hierarchical model, I can really just say that I'm fairly comfortable in talking about the quality of my inference.
That makes sense. Yeah, so for the computational complexity, let me revisit that topic. Will the way you do reduce the computational complexity for the dimension reduction step?
That's actually that's a great question, and the truth is that it won't. So the computational complexity is still quadratic. There's nothing that you can do about that. So all that matters is really the scale that you're working with. So in a previous slide that looks a lot like the one that I'm showing right now, the GPU results were flat, which might give you the impression that we actually have gotten around that quadratic complexity. But if you actually zoom in, and if you look at, now we're looking at the Hawkes process, you can see that the quadratic complexity is still there. It's just at a very different scale. So maybe you could say that we've cut the constant in half, or that we've done serious work to diminish that constant that's out front.
Okay, thank you.
Hi, Andrew. This is Mark Hancock. Welcome to UCLA, or at least it's the first time we've seen you, so it's great.
Thank you.
I had a question. It'd be interesting to try a different metric than the Euclidean metric, in essence, used here. And two ideas come to mind. One is using the spherical geometry of the planet much more. Not that it's necessary on a sphere, but that would seem to be relevant given the locations. Mm-hmm. And the other would be to use a dot product or a projection metric rather than the Euclidean metric. And the reason that's of interest is it sort of maps in very well with the idea of having locations on a sphere. And the second thing is it might lead to enormous computational advantages because it's a dot product. It's in essence linear, conditionally linear, and it could lead to dramatic computational improvements. So I just wondered if you could comment on either or both of those issues.
So my first response is not going to be very satisfactory to you, which is to say that it's not always fitting to be using this transportation network. So this is kind of an oblique response, so bear with me. What one might want to do, and this is something that as a statistician we're very comfortable with, is actually just to use a mixture model, a mixture of looking at these naive distances, which might be more important for positions that are very close together on the surface of the planet. And then let the model naturally select whether the appropriate distance is the air traffic distance or just the naive distance. The naive distance, of course, would take that spherical nature into account, although maybe not in a satisfactory way to you. So then my second response is that the inner product idea sounds very interesting, and that it's not immediately clear to me how that works in terms of a probability model, but maybe it's very straightforward. I just don't have the intuition for it at this moment.
Yeah, actually, that's not unsatisfactory, but I think it might work out well in the sense if you could have a Gaussian mixture on a sphere, so you have spherical Gaussian, then that would naturally work in. So that I think would be an interesting alternative model, and I think computationally it would lead to dramatic improvements. Yeah. But of course, it all depends on the details, and it could be some detail there that makes that not possible. But I think, in essence, doing Gibbs sampler updates where you condition on all of the x's via one would linearize a lot of the model.
Yeah. Well, this is work that I'm hoping to be involved in for the next decade or so, because there's so much room to run. So I look forward to discussing that aspect more.
Great, thanks. Great talk.
Thank you. Thanks.
And so also, Andrew, I have a technical question regarding the use of GPU. So I'm very curious about how that, so I'm not familiar with this because I thought that GPU is good at parallelization because so many cores, but on the other hand, it can only have simple operations on each core. So how would you do that in your setting, in your problem? How would you achieve that?
Yeah, that's a great question, and the answers can be a little bit subtle. The devils are really in the detail there. Mm-hmm. There's a lot of balancing of complexity and simplicity, and really what I would say is that this specific model and the general structure of an n-body problem with pairwise potential kind of gives you access to this stereotyped. So you're performing the exact same instruction set over batches of these that kind of contribute to these pairwise evaluations. So what I would say is that it's extremely model dependent. But what we know is that there's a couple kinds of models that are specifically very well, that a GPU is very well tuned for. So a large amount of matrix operations, that's great. Pairwise evaluations, that's great. And then some dynamic programming as well. You can get some significant speedups with a GPU.
And so for those things, do they have ready packages for use?
Yes, yes. Especially something like, sorry, I'm gonna need to have a little bit of water.
No problem.
So, I mean, first and foremost, matrix operations. That's, you know, there are CUDA libraries where CUDA is kind of the dominant framework, or you can think of it as an extension of C, written by NVIDIA and specifically tuned to NVIDIA hardware. So CUDA has some packages like cuBLAS, so that's CUDA basic linear algebra, and then another area, and this is still the matrix operations, but GPUs are just terrific for sparse matrix operations. So again, you've got here it's what's the relevant CUDA library? It escapes me now. So some of these are pre-written, and then, you know, there's certain physical models where, again, you can imagine that, you know, and my decision to, at the last level of abstraction, I want to think of this as simulating from a pairwise potential, or a potential function with these pairwise dependencies. This is extremely common in molecular dynamics, right? So actually, the physicists have known about the use of the GPU for this kind of thing a long time. And then what I've done is I've reinvented the wheel and then looked more into the GPU literature and said, well, gee, I probably should have cited some of the molecular dynamics literature, because you can think that really what I'm doing here is simulating a physical system.
Okay, thank you. Thank you very much. That's very good to know.
I love talking about this stuff, and I'm sorry if I'm being vague right now, but I'm always willing to go more into the details.
Yeah, it's very good to know that there are those resources available.
Yeah, there certainly are.
Okay, so any other questions from our audience, especially our graduate students? And also, by the way, Andrew, will you be willing to share your slides with us after?
Oh, of course.
Okay, that would be great. Thank you.
Of course. And I'm just, you know, even if you don't have a question now, well, first I invite anybody to ask questions now. I certainly have time. And then if a question occurs later, feel free, anybody can just feel free to reach out to me. I'm really excited about the opportunity to kind of, you know, look for shared interests. I feel like if you just think of data science at UCLA, it's all over the place. It's all over campus, and then I'm very excited to find collaborations and build collaborations.
Hi, Professor. I had a quick question. Most of this stuff is new to me, so thank you for the talk. It was really interesting. But on the inference on the diffusivity constant,
yeah,
the units are like square distance by year, right? Like it's done by year. I'm wondering, because blues are seasonal, does that impact how that inference is done, or like what the rate means?
Okay, so that's a great question. And I would actually contend that it does not, that the seasonality does not. And so if you'll allow me to, the reason that I'll say this is that we're conditioning on the phylogenetic tree. And the phylogenetic tree is kind of naturally taking into account this seasonality. And the reason that I would argue that it is because you kind of see these, and H3N2 is probably the best example of this. You kind of see this kind of bursting behavior, this kind of explosive behavior as these branches kind of just explode outward, but they do it almost in a seasonal in a seasonal manner if you look closely enough. So I would say that I would contend, and 80%, I would say yes, we take that seasonality into account.
Thank you.
But don't argue too strenuously against me, because then I might I don't know, I might end up contradicting myself.
Okay, do we have further questions before we finish today's talk? Yeah, so Andrew, thank you so much for your great talk today. So I think I'm going to share your slides with the students and the audience after I receive slides from you. And I hope that they can check further details that they didn't immediately understand during the talk. I think that will be a great learning process.
Yeah. Great, terrific. And thank you so much.
Thank you. And if we have further questions, please feel free to reach out to Andrew. Andrew is a faculty member in our Biostatistics department, and we really look forward to having more communications and possible collaborations with Andrew since we're on the same campus.
Terrific, thank you.
Thank you. Okay, so this will be the end of our last seminar this quarter. I think we will resume as our new quarter starts, but the organizer will not be me anymore. So I really thank you for your cooperation throughout this quarter.
And we should give Professor Lee congratulations for such a successful seminar series this quarter. So applause for Jessica Lee, yay.
Thank you, Mark. Okay, and thank you, everyone. Thank you, Andrew. Bye.
Okay.
Bye.
Thanks.
Bye.
Bye.
Bye.